Concrete is one of the most visually boring substances in human life, and that is part of why it hides its mystery so well. You walk across it, drive over it, build with it, lean against it, and almost never think about it again. A sidewalk hardens, a wall stands, a bridge opens, a floor dries enough to carry weight. The story appears complete. Whatever transformation needed to happen seems to have already happened. Wet became hard, soft became solid, process became object. Common sense closes the file. That is exactly the illusion this subject has to break, because concrete looks finished long before it actually is. The moment it appears still, we assume its important life is over. We imagine that setting is the end of the event, as though concrete were like spilled mud that merely lost its moisture and froze into place. From the outside, that belief feels perfectly reasonable. The surface becomes rigid. The shape stops changing. Workers move on. Buildings rise around it. Days pass, then years, then decades, and the concrete remains what it seems to be, fixed, silent, done. But inside the material, that certainty is far less secure. The first difficulty is emotional, not chemical. Human beings are deeply biased toward appearances that signal completion. If something no longer moves, we assume it has stopped changing. If something can bear weight, we assume it has finished becoming what it was meant to be. We do this with landscapes, buildings, bodies, and even with ourselves. Stability creates the feeling that process has ended. Concrete is one of the clearest examples of how misleading that instinct can be. What makes this so surprising is that concrete feels like the opposite of life. It does not breathe, heal, or grow in the biological sense. It belongs to the world of dead matter, of roads, pillars, foundations, and ruins. We expect interesting change from trees, clouds, skin, water, and weather. We do not expect it from a slab. A slab is supposed to be what remains after the interesting part is over, and yet some of the most astonishing facts in material science begin exactly there, because the hardening of concrete is not the clean ending it appears to be. It is more like the visible threshold of a much longer internal story. What you call set concrete is often only the stage at which the material becomes useful enough for human schedules. It is not necessarily the stage at which the deeper chemistry is complete. Strength can continue developing, internal structures can continue reorganizing, water can continue participating, unreacted particles can continue changing. Time itself can remain part of the material's evolution long after the eye has declared the process finished. That is why the title sounds so absurd at first. Concrete still getting harder after 2,000 years. It sounds like a trick, an exaggeration, or a dramatic way of saying that some old buildings happen to survive. But survival is not the same as continued development, and this is where the real wonder begins. The claim is not merely that concrete can last. The claim is that under the right conditions, it can continue becoming. Once that possibility enters the mind, the ordinary world changes a little. A sidewalk stops being just a sidewalk. A wall stops being only a wall. Ancient Roman harbors, domes, and breakwaters stop looking like relics of a finished past and start looking like evidence of a material process unfolding across centuries. But before any of that can make sense, one false idea has to be removed. Concrete does not harden because it simply dries out like mud under the sun. If that were true, the mystery would end almost immediately. So the next step is to ask a more precise question: what concrete actually is, and what invisible chemistry begins the moment water enters the mix? That matters because people start with the wrong picture. They imagine drying, waiting, and completion. The real story is stranger. Water does not merely leave the mixture, it wakes something inside it, and that awakening lasts longer than common sense expects. The first mistake most people make about concrete is simple. They confuse hardening with drying. That sounds harmless, but it quietly ruins the whole subject. Drying suggests that water is merely escaping, leaving the material behind like mud left in the sun. If that were true, concrete would be interesting only for a short while. It would begin wet, lose moisture, and finish hard because the liquid was gone. But concrete does not become solid that way. In fact, the most important role of water is not to leave, it is to react. To see why, you have to separate concrete into its parts. Concrete is not one substance. It is a composite material made from aggregate, usually sand and stone, mixed with cement and water. The aggregate provides bulk and structure. The cement is the chemically active ingredient, and water is not just there to make the mixture pourable. Water is the trigger that starts the transformation. Cement, especially ordinary Portland cement, contains compounds rich in calcium, silicon, aluminum, and iron. On their own, these powdered minerals are relatively stable, but when water is added, they begin a series of reactions known as hydration. That word matters. Hydration does not mean simple wetness. It means water is entering into chemical relationships with the cement compounds, breaking bonds, forming new products, and reorganizing the material from the inside. This is the first real shift in understanding. Wet concrete is not like wet dirt waiting to dry. It is more like a packed field of reactive mineral grains about to build something new. The water penetrates the cement particles, dissolves some components, and allows new crystalline and gel-like structures to form. These new structures grow outward, interlock, and gradually bind the sand and stone into a coherent solid mass. One of the most important products of this process is calcium silicate hydrate, often abbreviated as CSH. It is not a dramatic name, but it is one of the reasons modern cities stand. CSH forms as hydration proceeds, and it becomes the glue-like binding phase that gives hardened concrete much of its strength. Another product, calcium hydroxide, also forms, along with other compounds depending on the cement chemistry. What matters for the viewer is not memorizing names, but understanding the principle. Concrete becomes hard because new mineral structures are literally forming inside it. That is why the surface behavior can be misleading. A concrete slab may appear to dry and become solid enough to walk on within a relatively short time, but the internal chemistry has not ended just because the surface looks finished. Setting and hardening are not identical events. Setting is the loss of plasticity, the point at which the mixture is no longer fluid. Hardening is the longer increase in strength as hydration products continue developing and filling space within the material. This also explains a fact that surprises many people. Concrete often needs moisture to cure properly. If it loses water too quickly, the chemistry can be interrupted. That is why fresh concrete is often kept damp, covered, or otherwise protected during curing. To someone who thinks hardening means drying, this looks contradictory. Why keep adding or preserving water if you want the material to become solid? The answer is that you are not trying to evaporate the water away as fast as possible. You are trying to give the chemistry time to proceed. In other words, the strength of concrete does not come from water leaving. It comes from water helping create internal bonds that did not exist before. The liquid is not merely a temporary guest. It is part of the architecture of the final material. There is a practical reason this misunderstanding survives. Human construction schedules care about when forms can be removed, when surfaces can be walked on, and when structures can bear load. Those are useful milestones, but they are not the same thing as chemical completion. A builder may say the concrete is ready, and within that context, it is. Yet from the perspective of material science, readiness is not finality. A bridge deck can be functional while hydration continues. A wall can stand while its internal microstructure is still densifying. Human use measures convenience. Chemistry measures transformation. And those two clocks do not stop at the same moment. That gap between appearance and process is the key to understanding why concrete's story can stretch beyond setting. Once you understand that concrete hardens through hydration rather than simple drying, a more surprising possibility opens up. If hardening comes from ongoing chemical reaction, then the apparent stillness of a finished slab tells you much less than you thought. A sidewalk may feel complete, a wall may look inert, a bridge column may seem like the very image of solid finality, but none of those appearances can tell you by themselves whether the internal chemistry has truly finished. In many cases it is not. That is the hidden life of concrete. What looks static at human scale can remain active at microscopic scale for a very long time. Not dramatically active, not in a way the eye can catch from one day to the next, but active enough that the material's internal structure can keep evolving after construction crews are gone, after scaffolding is removed, and after people begin treating the structure as part of the permanent world. The reason begins with a simple fact. Not every cement particle reacts immediately. When water is first mixed with cement, hydration begins at the surfaces of the particles. Reaction products form around them, creating shells, gels, crystals, and complex microstructures. Some particles react quickly, some react more slowly. Some remain only partially hydrated, especially deep inside the matrix, where access to water, space, and reaction pathways becomes more complicated. So even in concrete that has become hard enough for practical use, islands of unreacted or partially reacted material can remain embedded inside. If moisture is available over time, some of those particles can continue reacting. This matters because each additional stage of hydration can generate more binding phases, fill more microscopic space, and increase the density of the internal structure. The process is not infinite, and it is not uniform, but it is real. Concrete can keep developing because the chemical opportunity for further reaction has not necessarily disappeared just because the material feels solid. At the same time, the material's pore network also changes. Freshly placed concrete contains water-filled spaces of different sizes, channels left by mixture proportions, and voids that influence strength and durability. As hydration continues, some of those spaces are partially filled by reaction products. Capillary pores can become narrower. Connectivity within the pore system can change. The microstructure can become denser, less permeable, and in some cases mechanically stronger. That shift is easy to miss because from the outside nothing seems to move. Yet at the microscopic level, the material is negotiating with water, minerals, and geometry. Crystal growth plays a role as well. The hydrated cement matrix is not an amorphous dead block. It contains phases that can nucleate, expand, and organize over time under the right conditions. Tiny mineral formations can grow into pores, bridge spaces, or alter the local arrangement of stresses and pathways within the material. Again, this is not growth in the biological sense. Concrete is not alive, but matter does not need to be alive to remain dynamic. All it needs is a chemistry that has not fully exhausted itself. This is why curing conditions matter so much. Concrete that dries too quickly may lock in a less complete internal development. Concrete that remains properly moist for longer periods can continue hydrating more effectively, producing a more mature structure. Time and water are not just external circumstances. They are partners in the material's becoming. Human schedules usually focus on 7 days, 28 days, or other engineering milestones because strength testing needs practical benchmarks. But chemistry is not obligated to stop at the benchmark simply because paperwork does. The really important contrast is this: what engineers call set, or even cured enough, does not mean finished in every meaningful internal sense. It means finished enough for a defined purpose under defined conditions. That is a human threshold, not an ultimate one. The material itself may still be changing quietly, especially if environmental conditions continue feeding slow reactions, mineral adjustments, or poor evolution. This helps explain why long-term performance in concrete can be more complicated than a simple decline narrative. We often assume time only erodes. Sometimes it does. Freeze-thaw damage, chemical attack, cracking, and corrosion can all degrade concrete. But time can also permit continuing internal development, especially where the chemistry and environment favor it. Strength gain can continue beyond the early curing period. Internal densification can continue. Certain microstructural features can become more stable. The material may not just be surviving time, in some respects, it may be using time. That idea feels strange because it violates our ordinary picture of solid matter. We think solid means finished. We think hard means complete. Concrete teaches a different lesson. A material can be load-bearing, rigid, and apparently final while still carrying unfinished processes inside it. It can wear the mask of permanence while remaining chemically unsettled at scales too small for intuition to register. One more subtle process matters here. Moisture does not only enable hydration directly, it also controls the mobility of ions within the concrete. Dissolved calcium, silica, and other components can migrate over tiny distances and precipitate in new locations, slowly reshaping the material's internal balance. In some contexts, this can help seal microvoids or reinforce local structure. In others, it can create stresses or vulnerabilities. The point is not that every long-term change is beneficial. The point is that concrete remains a chemically negotiable system long after our eyes classify it as finished. So when people say concrete is just sitting there, they are describing the scale of their own perception, not the full truth of the material. Beneath that stillness lies a slower chronology, one measured in hydration fronts, pore refinement, crystal formation, and gradual mineral reorganization. The slab does not announce these changes, it simply continues, molecule by molecule, to decide what kind of solid it will become under water, chemistry, and time. That quiet persistence is the surprise hidden inside ordinary concrete. The story becomes truly extraordinary when it leaves the modern sidewalk and enters the ancient world. It is one thing to say that ordinary concrete can continue developing internally for months or years under the right conditions. It is another to look at Roman harbors, seawalls, piers, and domes that have endured for centuries or even millennia, and realize that time itself may have helped preserve them. At that point, concrete stops being merely a useful building material and starts looking like a lesson in how matter can collaborate with history. Roman concrete is not identical to modern Portland cement concrete. That difference matters enormously. Many Roman builders used a mixture that combined lime with volcanic ash, especially pozzolanic ash from regions around the Bay of Naples. When this material reacted with water, it produced binding phases different from those dominating most modern formulations. The Romans did not speak in the language of modern chemistry, but they had discovered, through practice, a recipe that created remarkable durability. What looked like practical engineering was also a kind of material wisdom. The volcanic ash was crucial because it contained reactive silica and alumina. In the presence of lime and water, these ingredients could form durable calcium aluminum silicate hydrates and related mineral structures. In marine environments, the chemistry became even stranger and more impressive. Seawater, which modern engineers often treat as the enemy of concrete and steel, could participate in reactions that slowly generated additional mineral growth within Roman harbor structures. Instead of simply eroding the material from the inside, the environment sometimes became part of its continued development. That is the astonishing inversion Roman concrete presents. We usually think of time and exposure as agents of decay. Saltwater attacks, waves wear down, cracks spread, materials age by losing their integrity, and often that is true. But Roman concrete reveals a more subtle possibility. Under the right chemical conditions, time does not merely subtract from a material. Time can become one of the conditions under which the material matures. Researchers studying ancient samples have found evidence of long-term mineral formation inside Roman marine concrete, including crystals such as aluminous tobermarite and related phases in certain contexts. What matters most for the viewer is not memorizing the names, but understanding the principle. The material did not simply harden once and then spend 2,000 years trying not to die. It continued interacting with water, dissolved components, and surrounding conditions in ways that could reinforce or stabilize its internal structure over extremely long periods. In other words, Roman concrete complicates the whole idea of durability. Durability is often imagined as successful resistance to change. A durable thing is something that stays the same while time tries to destroy it. But Roman concrete suggests that some forms of durability arise not from resisting change altogether, but from changing well. The material survives because it remains chemically responsive in a beneficial direction. It does not defeat time by becoming perfectly inert. It uses time by remaining slowly reactive. Seen this way, a Roman harbor wall is not just a survivor from the past. It is a record of a process stretched across centuries in which minerals, water, porosity, and stress kept interacting long after the builders were gone. The structure endured because its chemistry kept participating. That makes Roman concrete scientifically important in a way that goes beyond archaeology. It offers a counterintuitive model for material design. Instead of asking only how to create a substance that freezes into permanence as quickly as possible, it invites a different question. Can we create materials that continue improving, or at least stabilizing themselves, under the very conditions that normally destroy them? Can endurance come not from shutting chemistry down, but from guiding long-term chemistry wisely? This is part of why modern researchers remain fascinated by Roman formulations. They are not chasing nostalgia. They are trying to understand a deeper principle, that matter can be engineered not only for initial strength, but for long collaboration with environment and time. The Romans, through empirical practice rather than modern theory, appear to have produced mixtures in which exposure to seawater sometimes drove additional mineral organization instead of simple collapse. That is an astonishing achievement, and it challenges the modern bias toward thinking that all aging is merely decline. It also deepens the philosophical meaning of the whole subject. Concrete usually stands in the imagination as the symbol of dead infrastructure, Roads, parking garages, retaining walls, anonymous foundations. Roman concrete disrupts that image. It reminds us that even the most apparently lifeless materials may contain long stories of reaction, adaptation, and negotiation hidden within them. A pier in ancient water is not just surviving by luck. It may be carrying on a conversation with its environment at a speed too slow for ordinary perception. And this is why Feynman would have loved the lesson. The world keeps refusing the categories we lazily assign to it. Dead matter is not always dead in the way we mean. A finished object is not always chemically finished. Time is not always the enemy of form. Under the right circumstances, the very force we assume must destroy a thing can help complete it. So Roman concrete is more than a historical curiosity. It is proof that material reality can be stranger, slower, and more intelligent than common sense expects. It shows that some substances do not merely endure time as passive victims. They incorporate time into their own becoming. And once you see that, the old image of concrete as frozen, inert, and final becomes impossible to trust in quite the same way again. By the time you understand concrete in its deeper sense, it becomes difficult to look at any slab, wall, column, or ruin in quite the old way again. The ordinary image no longer holds. Concrete is no longer just the gray symbol of finality, the material of sidewalks, foundations, overpasses, and forgotten structures. It becomes something stranger, a reminder that stillness and completion are not the same thing, and that some of the most apparently finished things in the world may still be participating in long, hidden processes far below the threshold of human notice. That shift matters because it reaches beyond concrete itself. Concrete is a lesson in the danger of trusting surfaces too completely. We see a hardened material and assume the story is over. We mistake usefulness for completion, stability for finality, silence for inactivity. The slab does not move, so we say it is done. The wall bears weight, so we call it finished. The ancient structure remains standing, so we assume it has merely resisted change. But the chemistry of concrete reveals a subtler truth. A thing can look settled and still be evolving. It can appear complete and still be negotiating with water, minerals, pores, stress, and time. This is one of the deeper patterns of the physical world. Matter often hides its activity behind apparent stillness. Mountains look permanent, while erosion reshapes them grain by grain. Metal looks solid, while oxidation slowly alters it. Bone looks fixed, while living cells continually remove and rebuild it. Even the human body feels stable from day to day while proteins turn over, cells repair damage, and structures age in place. Concrete belongs to this same family of hidden change. Its stillness is real at one scale, but incomplete at another. That is why the material is so philosophically satisfying. It gives a hard, physical example of something people often recognize only abstractly. The world is full of processes wearing the mask of objects. We live among things we call finished because our senses are calibrated for immediate practical life, not for microscopic or century-long transformation. A road must either support a car or fail. A bridge must either stand or collapse. A floor must either bear weight or crack. Human life measures utility in short intervals. Chemistry does not. Chemistry continues according to conditions, pathways, and opportunities, whether or not our schedules have moved on. Seen from that perspective, concrete becomes almost a rebuke to impatience. It reminds us that reality is not obligated to organize itself around the timescale of human attention. A day is enough for us to say something has dried. A month is enough for engineers to test certain strengths. A year is enough for people to forget the material ever changed at all. Yet inside the concrete, the chronology may be longer, slower, and more patient than our categories allow. It may continue resolving unfinished chemistry, densifying structure, shifting pore networks, and interacting with environment in ways too gradual for intuition to honor. This is also why Roman concrete feels so powerful as an example. It turns hidden process into civilizational evidence. It shows that time does not always function only as erosion. Under the right conditions, time becomes part of material development. That possibility is both scientifically useful and emotionally haunting. We are trained to think of time as what weakens, what wears, what subtracts. Roman concrete forces a more complicated picture. Sometimes time destroys, sometimes it reveals weakness, but sometimes under particular chemistries, time participates in strength. And that returns us to the deepest contrast in the whole subject. Concrete seems like one of the deadest materials in the built world, yet it teaches one of the most lifelike lessons in matter. What endures is often not what resists all change, but what changes in the right way. A durable thing is not always the thing that becomes perfectly inert. Sometimes it is the thing that remains responsive without collapsing, that keeps negotiating with its environment without losing its coherence, that slowly completes itself while appearing already complete. There is something almost existential in that. Human beings also tend to misread completion. We imagine that maturity means becoming fixed, final, beyond process. But the world keeps teaching the opposite lesson. Bodies keep changing. Minds keep changing. Relationships keep changing. Materials keep changing. The strongest things are often not the things that stopped evolving, but the things whose changes remained structurally meaningful over time. Concrete, of all things, becomes a witness to that truth. So the final insight is not merely that concrete can keep getting harder. It is that the world is more active beneath stillness than our instincts admit. The sidewalk under your feet, the bridge above your road, the old harbor wall in salt water, the dome that outlived empires, all of them suggest the same quiet revelation. Solidity is not always the end of becoming. Sometimes solidity is just what becoming looks like when it slows down enough to resemble permanence.